Black holes, where time and space converge under gravity's immutable power. These extremes of nature, once considered improbable, are now giving up their secrets. In fact, scientists have been able to imagine the impossible, the black hole at the center of our galaxy. We can now peer into the abyss. The concept of black holes was first proposed by the German astronomer and physicist Karl Schwarzschild, barely a year after Albert Einstein had published his works on the field equations of gravitation in 1915. Schwarzschild wrote to Einstein from the German trenches of the First World War, detailing his mathematical results of his gravitational equations. Sadly, the brilliant scientist later succumbed to a skin disease he contracted in the trenches at the age of 42. The existence of these so-called frozen stars was written about and debated for 50 years. In 1967, physicist John Wheeler coined the term black hole to describe these impossible objects and the conditions that would create them. New Zealander Roy Kerr advanced the concept by publishing a solution to the equations, which would require that black holes spin like all other astronomical bodies. Then Stephen Hawking and Roger Penrose theorized that black holes could emit radiation, now called Hawking radiation. The theory: if a black hole had no material to absorb and grow, then a black hole could evaporate, effectively shrink and die. All scientists had to do was find one to study. Quasars, the tremendously bright, distant objects, were factored in as a strong case for black hole accretion, the only imaginable energy source capable of such incredible luminosity. In 1964, astronomers discovered one of the brightest X-ray sources in the sky in the constellation Cygnus, and labeled Cygnus X1. The powerful source didn't coincide with any bright optical or radio source, leaving it in the mystery basket of observations. Before long, with advancements in computers and space-based telescopes like Hubble, black holes were eventually detected, or their effect on their surrounds were detected, as black holes by their nature can't be seen.
Black holes are these incredibly fascinating but mysterious objects. We know they sit at the hearts of galaxies, and they drive how those galaxies grow and how those galaxies die. They swallow gas and stars up. They're also these incredibly enigmatic and mysterious objects that live at the boundary between our two great theories of physics: general relativity, which describes gravity, and quantum mechanics, which describes the smallest things in the world.
Black holes are literally gravity run amok. They are purely gravitational objects predicted by Einstein's theory of general relativity, and their most notable and terrifying feature is that things go in and they never come back out.
Wonder comes to my mind first. Such objects were never expected to exist in nature until very recently. As a matter of fact, I was a complete skeptic about black holes as recently as 20 years ago.
Black holes are places where Einstein's theory of general relativity is the whole story, not merely a perturbation on top of Newton's theory, which explains the dynamics of planets in our solar system. As a result, black holes provide a unique environment in which to probe general relativity specifically and strong gravity generally, and its implications across the cosmos.
If you want to make a test of the fundamental theories of the universe, you want to go to the most extreme laboratories in the universe. And a black hole is that.
Seeing a black hole actually allows us to not only know they exist, and not only know an event horizon exists, It also allows us to test some of the very basic predictions of the theory of general relativity of Albert Einstein, which really describes space and time in its completeness. And that has never been tested before.
If you like Einstein's theory of gravity, then black holes are, one of the most interesting examples of this theory. And this is my role within this project. I am a theorist. I work with equations and simulations, and my role is that to try and understand whether the image that we produce corresponds to the predictions of Einstein's theory or maybe to something else.
From the physics side, I find that more an interesting question, that this is basically some kind of rent or tear maybe in space-time, and a place where we don't understand the physics and have a lot of serious questions about information theory.
I was very excited the first time I saw the first image. For a long time, this was purely theoretical. We were predicting that we would see certain features in the image, but we didn't really know, was it really there? And now we know, and it was exciting that all of that uncertainty collapsed in that moment.
So as the magnetized gas is falling onto the black hole, it heats up and therefore generates the light that we then see. Now, from our daily experience, we expect that light travels on straight paths and straight trajectories. We call them rays. Here, the situation is very different. We have a black hole sitting right there. So what the black hole is doing, it is deflecting and bending the light rays away from the straight paths that we understand in our daily life. And in fact, it can be so strong that we can see things that are behind the black hole that we thought are obstructed by it, just because the black hole is bending the light rays into our line of sight.
Scientists began running simulations on supercomputers. Multiple computational models were visualized to better understand what they might find in the data collected from their observations.
After we computed the radiative signature of our simulations, we have to compare them to the observations. And this can be imagined as you are in a stadium during a football match, and you have an image. And you want to figure out if this person or whatever is on this image is among the spectators in the stadium. So what you do is you take this image and try to match it with all the 60,000 spectators in the stadium. And you do this while you rotate it, you scale it, you increase the contrast, and you try to figure out first what is on your image. Is it a person, is it a cat or whatever? And try to match this to the spectators. And this seems trivial, but it's not. It's a highly computational, demanding process. So we need a supercomputer, which we have in Frankfurt. And we developed a so-called genetic algorithm, which is a very smart way running through these images and try to adjust them. And this takes roughly a month. And after this calculation time, we have maybe 10 of those spectators which match your image. And this is very similar to what we do in the EHT. So we try to compare and match our observations with the theoretical predictions.
So what is most surprising of this experience is that we managed to get a very good image the first time we tried to synchronize all of these telescopes at the same time. It is not so surprising that we obtained the image that we had predicted through simulations because, well, we believe our simulations are correct and because we believe that the theory of Einstein's general relativity is the correct one.
In 2019, they achieved their result, an image of the shadow of a massive black hole in the distant M87 galaxy. It was a world-first achievement celebrated around the globe.
I think we've been extremely lucky. I'd expected that we have to work for years and years, do many observations until we get a final image. And then we look at our first source and we see that ring. We see the event horizon and we see that shadow, that dark region And you know immediately we're looking at an event horizon at a black hole from all sides at once in this thing. We see at a region where time stops. This is a very different part of the universe that we're seeing for the very first time.
We wanted to take an image of a black hole, and the problem with black holes is that they are very small. So you want to take a very big black hole, which unfortunately is very far away from us. And so you need a big telescope. This telescope is 100 meters in diameter, but it's not enough. You want a bigger telescope, and of course it's impossible to build, but you can create a virtual telescope by joining different telescopes in different locations, and so you can build a telescope which is as big as the Earth. And in fact, that's exactly what we've done. We joined telescope like this with telescope on the United States, and one even in the South Pole, to get a very sharp image. An image that is comparable to seeing an orange on the moon. Black holes tell you that there are regions inside them that cannot be explored. And for a physicist, this is very disturbing and attractive at the same time, because we don't like to have doors which we cannot cross. And in particular, inside black holes, physics is even expected to fail completely. And so this even adds fascination to these objects.
The future of the project will hopefully going towards a new understanding of more fundamental questions in physics. If this is true that black holes are the extreme objects where we can study gravity, and we know that general relativity, which describes black holes in the outer part up to the event horizon, breaks down at the event horizon. So the big hope is that with more data we might be able to study the physics beyond general relativity. So maybe there might be quantum physics ruling beyond the event horizon, or the combination of quantum physics and general relativity, which would be the theory of quantum gravity, which is non-existent at the moment, but we might learn more about this with the help of studying black holes.
Our experiments are like an Arctic expedition. We have to plan for months and months and months in advance, gather our equipment, and then we have this great migration of people to observatories all around the world. We stay up all night, we run our telescopes, and then we have this terrible period of waiting where we don't know if it's all worked. We send all of our data together, and only when it's truly combined do we know if it's worked. And then the even harder part begins of analyzing that data and being very, very careful, doing all the checks and balances to know that we got it right.
Data analysis, imaging black holes, and doing simulations is very exciting. It's also very difficult and requires a lot of patience. It's a very long process, but seeing the final product is very satisfying.
The Event Horizon Telescope collaboration is this amazing group of fantastic people from all around the world. Americans, Europeans, people from Asia, who've come together with all their technical expertise and scientific expertise to make this image of a ring around the black hole. The future of this project is amazing, because now that we've seen what we're after, we have so many more questions to ask about it, to push into the regime of, can we decide, is Einstein right? Can we study how gas really gets swallowed by the black hole? Can we see a giant eruption of radiation, of particles coming out of the system? So many things to do. We've really only just begun.
Now we want to make the first movie. Now we want to understand how space-time rotates around the black hole. We'll do that by putting more telescopes around the world to make our virtual lens even better.
It was a fantastic way of combining talents from different people in a way that otherwise would have not been possible. In order to take this picture, you need the cooperation, the simultaneous observations of many radio telescopes across the planet. You need to have the largest possible network of telescopes taking the same image at the same time.
New goals for the Event Horizon Telescope were quickly set. The M87 massive black hole is far away from Earth. Scientists wanted to get a closer look and decided to image another black hole at the center of a galaxy, one much closer but also much smaller and shrouded in gas and dust.
So if you try to look into the center of galaxies, it's usually blocked from view by dust and other stuff. In the radio, you can look through, like here today, we can look through rain, you can look through clouds, and so we can look through dust. And with combining radio telescope like this together with other telescopes in the world, you can peer right into the center of the galaxy and see this black hole.
The science result is it's just one point in time in the project, and we are always learning more about how the instrument works, how people work, how new theories come about, and so this is an evolution in my perspective. It's not just one point in time where you say, this is it, that's done. It always continues.
So we still have a lot of mysteries to be solved, problems to be tackled. There are still many questions about black holes, so I would like to study further the black holes.
The Event Horizon Telescope targeted the black hole in Sagittarius A, which is the location of the center of our very own Milky Way galaxy.
The long-term future of experiments like the Event Horizon Telescope is moving this kind of instrument into space and starting imaging black holes from space, which improves a lot this kind of observation because it allows us to have even higher angular resolution than what we have now. So we will be able, maybe in 20 years, 30 years, make a very accurate images of the event horizon of a black hole.
Not only did scientists image the black hole, they sampled the radio emissions from the surrounding hot gases, giving us an audio impression, the sounds of a black hole.
So far, we've been looking at the closest massive black hole, but quasars, very distant from us, with gravity, we can see the motion of gas and resolve the sizes of these regions and thereby measure then the mass precisely. So if you can do this for many quasars, many distant objects, then you can solve perhaps the riddle how massive black holes played a role in the evolution of galaxies. We now know that basically every galaxy has at its center a massive black hole of different masses. We'd like to understand that in detail. There is, if you like, a symbiosis between these black holes and galaxies, and we need to understand that in order to understand the evolution of the universe.
Studying the data from the Event Horizon Telescope continues to reveal more detail, in this case X-ray emissions, reveal magnetic lines of force through the orbiting gas clouds. Further study of the X-ray emissions is currently underway with a new space-based X-ray observatory, the Imaging X-ray Polarimetry Explorer, or XP. Launched in 2021, XP is designed to observe extreme cosmic objects like pulsars, neutron stars, and black holes. This satellite is able to study X-ray radiation, which is polarized or oscillating in a particular direction. This reveals more detail of the physics of these high-temperature environments, particularly around black holes.
But there are two other parameters that we could look at if we only had the tools to do that, and those have to do with the polarization, the degree of polarization, and the position angle, the angle associated with the polarization. So by doing this mission, we're opening up 2 more degrees of freedom to be able to try to understand how are the X-rays produced, what are the models. We have to be able to predict the polarization that we will turn out to measure. So it's really exciting. Our science working group has studied we have 7 different teams of studying different classes. So for example, the radio pulsars, supernova remnants, etc. And so we're going to be looking at 7 different classes and several examples of those classes so that we get a good preliminary survey of what polarization is out there.
The extreme environments created by black holes are an opportunity to study many other phenomena. Neutrinos, the most abundant particles in the universe, have almost no mass and very rarely interact with matter. They seem to be generated in extreme objects like exploding stars and the fast particle jets ejected by supermassive black holes. Colliding black holes are another event closely watched, as they generate gravity waves that ripple through space-time and can be detected here on Earth. Another recent event detected was the flipping of the magnetic field surrounding a massive black hole. The reversing polarity caused the visual brightening of the material surrounding the black hole and the reduction of its X-ray emissions. During this time, the X-ray corona disappeared, and only when the flipped magnetic field gained strength did the X-rays emissions recover. Another black hole has been observed devouring a star that wandered too close, the ejected superfast jets of material interacting with nearby dust clouds and aiding to form planets within the material. These singularities appear to be an intrinsic part of both the destruction and creation of stars and planets. While we don't have all the answers, discoveries like this one set us on a path to understanding more about the universe. The search for life within our solar system continues unabated. Scientists are following the signs for water, either deep oceans or hot springs where life can evolve. There are exciting candidates to explore: the icy moons of Jupiter, oceans in the sky. Orbiting the giant Jupiter are 3 prime candidates. Ganymede, the largest moon in the solar system, Callisto, once thought to be dead, may harbour a salty ocean. And the active Europa, with its plumes of water erupting into space. The European Space Agency is about to launch a probe to investigate these 3 potential sites. A daring mission called JUICE.
JUICE is the Jupiter Icy Moon Explorer. So it's the first large mission of the Cosmic Vision program of the European Space Agency, and has the objective to study the Jupiter system and 3 of the Galilean moons, 3 icy moons, which are Europa, Galileo, Ganymede, and Callisto.
This mission is of particular importance for the European industry because this is the first time that Europe is going to Jupiter. So we are supporting the European Space Agency and beyond the European scientific community in their endeavor to go to Jupiter and explore Jupiter and their moons.
The scientific objectives of JUICE are multiple. So first of all, humanity always poses itself a question, are we alone in the universe? Is there life outside Earth? To respond to this question, first we need to answer to another question. Are environments where life can be sustained before going and search for life? And this is one of the main objectives for JUICE, to search if on the environment, on the ocean world of Europa and Ganymede, there are the conditions to sustain life. Now, from the past missions, we know that some of these conditions are fulfilled, and we want to go with JUICE to investigate even deeper and to make sure that these conditions are there. And these conditions are, for example, there is water, there is liquid water, there is a source of energy inside the planets, so there is energy. There are the chemical compounds which are needed to sustain life, the life as we know, so based on carbon. And is a protected, is a stable environment because it's under the crust of the moons. So once these 4 elements are fulfilled, there is the probability that life will be sustained outside Earth is very high. The other objective of JUICE is to study the Jupiter system in its integrality, as seen as a miniaturized solar system, if you want. We have a gas giant with bodies that go around this body, and studying the interaction of the gas giant with these bodies, we can understand better, for example, the development of our solar system, how it was born, how it works, and etc.
So JUICE is a very exciting mission. So we are going to explore Jupiter in details. And in particular, I would like to know whether there are conditions hospitable for life around a gas giant like Jupiter. And we are going to focus that on the 3 icy moons, which are Europa, Ganymede, and Callisto. And we would like to know whether inside those moons there are conditions which are interesting for life. And we are going in particular to explore the liquid water which are underneath the crust of those moons.
In the past, there were other missions that they analyzed the Jupiter system, like Galileo, for example, has given us important information to build the JUICE mission. There is also Cassini that passed by, that we gather a lot of data also from it, and also from observation from Earth, also observation from Hubble, for example, has provided us a lot of data which are precious to build JUICE and to build also the profile of the mission, to know what we are going to study.
We have in total 10 scientific instruments on JUICE. And basically we will observe Jupiter and its moons in all possible wavelengths and type of observations that we can do. So we have a number of telescopes in all wavelengths, visible, infrared, ultraviolet. We have a radiometer to sense the atmosphere, the structure of winds of Jupiter and their moons. and we have electric and magnetic sensors. Some of them will be deployed at the tip of a magnetometer boom. So RIME is this big antenna that you see there deployed just behind us. It is a radar antenna that is working at a very low wavelength, 9 megahertz. So for that to happen, you need a very long piece of antenna that will be able to sound very deep below the surface, the internal structure of the moons, in particular Europa, Callisto and Ganymede. The objective is to try and locate the liquid water ocean that is underneath the icy crust of these moons. As of today, we are still not sure how deep we have to dig, let's say, to find this ocean, and this antenna will help us figure out at which depth we can find this ocean.
At the moment, the nominal science is foreseen to last 4 years. In these 4 years, Jupiter will make all the investigation. It will make some flybys of Europa, flybys of Callisto, and then we'll go into the details of the analysis of Ganymede. We'll stay in orbit around Ganymede for a good part of the Jupiter tour.
JUICE will start its science mission about 6 months prior to entering orbit around Jupiter, making observations as it approaches its destination. Once in the Jovian system, a gravity-assist flyby of Jupiter's largest moon, Ganymede, also the largest moon in the solar system, will help JUICE enter orbit around the gas giant. During its operations, the probe will make 2 flybys of Europa in July 2032. Europa has the strongest evidence of an ocean of liquid water under its icy shell. JUICE will study the moon's active zones, surface composition, geology, and the plasma environment around the moon. A sequence of Callisto flybys will then be used to study this ancient cratered world that may also harbor a subsurface ocean, but will also change the angle of JUICE's orbit, making it possible to investigate the polar regions of Jupiter. Now that the probe is fully assembled, it has to be thoroughly flight tested to ensure its survivability, because the giant's magnetosphere traps an intense and dangerous radiation environment.
This milestone is very important because here we have the spacecraft. It's integrated, it's ready. We have all the 10 instruments are delivered, are there. All the platform units are there, the antennas is all in place. So the spacecraft is ready for the test campaign to verify finally that everything's worked as expected within the performances they were expecting. And this is 1 year from launch. So this is a very important milestone. The spacecraft integrated is there, and we can carry on with the test phase.
So we start first with electromagnetic compatibility test. The goal is to verify that the spacecraft has a sufficiently low level of electromagnetic perturbations, because a number of instruments of JUICE will sense electric and magnetic fields at Jupiter, and we do not want the spacecraft to be a source of perturbation for that. After that, we will do a number of mechanical tests. It will be done over summer. Here the goal is to verify that the spacecraft can survive the launch environment that will be imposed by Ariane 5 when we will launch to Jupiter.
It is true that the JUICE spacecraft that we can see on the background is going to be launched in space, meaning that it's not like for aircraft. We can repair something after a couple of hours of working. We need to make sure that before we launch, everything will work properly as expected.
And then there will be additional tests, like a vibration test, including with the solar array, so that will be quite exciting. We have also what we call EMC test, so to make sure that the spacecraft is quiet from the electromagnetic point of view. It's very important for the science of the mission. And additional tests like a communication between the spacecraft and the ESOC flight control team that will need to control the spacecraft once it flies. So all these tests will take place in the coming 10 months. And after that, hopefully the spacecraft will be declared ready for launch, and we will ship the spacecraft to its final destination on Earth, which is the French Guiana spaceport.
Replicating the environs of space is no easy task here on Earth. At ESA's test center, ESTEC, in the Netherlands, is the Large Space Simulator, which can model the vacuum of space and simulate both the extreme heat and cold of deep space. It is Europe's largest vacuum chamber, and its internal black panels, which are filled with liquid nitrogen, were used to cool the environment down to around -180 degrees Celsius. To test against extreme heat, lamps are used to raise the temperature up to 250 degrees Celsius.
JUICE, in order to fly to Jupiter, will do some gravity assist around several planets, among them the Earth and Venus, which is very close to the Sun. And in fact, all the electronics inside the spacecraft are supposed to work properly in a certain range of temperature, and the thermal design of the JUICE spacecraft aims at protecting this unit from the very harsh environment, cold or hot, for this unit in order for them to work properly when we will start to do science at the Jupiter icy moons.
To reproduce the heat side of space, so when we go close to the Sun, we simulate the Sun. And in order to do so, we have a set of lamps, very powerful lamps that are reflected in 121 mirrors that can be reconfigured depending on the mission characteristics. And in this case, we simulate the heat of the Sun while the spacecraft goes through Venus. Why Venus? Because the JUICE mission is doing a flyby in Venus before going finally to Jupiter.
Yeah, so when I saw JUICE going to the space simulator, I had a mixed feeling, of course, because it was a very scary moment. It's a little bit like your baby spacecraft, so you're a bit scared that something will go wrong. But at the same time, you know that the team, in particular, the test center people, they know what they are doing, so it's quite a secure activity. So it was a mixed feeling, but you always feel nervous when you see the spacecraft going into the large space simulator.
And in addition to that, we have also some requirements coming from the environment itself of Jupiter, like temperature and radiation. Jupiter is a very aggressive radiation environment that is making the whole design of a spacecraft even more complex.
Jupiter has the largest magnetosphere in the solar system, 18,000 times more powerful than Earth's. In combination with the sulfur dioxide ejected by the Moon, the space around Jupiter is loaded with plasma. The magnetosphere also traps and accelerates particles, forming an intense radiation field that is thousands of times more powerful than Earth's Van Allen belt. The result is a very hazardous environment for spacecraft and potentially humans.
After that, we will also test the propulsion system in order to be sure that it is leak-tight and fully operational when placed into a flight configuration. We will do a second thermal vacuum test in a chamber very close to this facility in October in order to verify in pressure and temperature conditions and full flight configuration that the spacecraft is behaving nominally in all functions. And finally, after having tested the spacecraft in all these various environments, we will verify a last time that from a functional perspective, the spacecraft behaves nominally and is ready for shipment to the launch site.
That launch site is Europe's spaceport in Kourou in French Guiana, where the venerable Ariane 5 will lift JUICE into space. It will also be the final launch of the Ariane 5 rocket series, one of the most reliable launch systems, with 112 launches and just 5 partial or complete failures. The Ariane 5 heavy lift vehicle has launched many of the most important space probes, including the Rosetta mission and most recently the Webb Space Telescope. It It will be replaced by the Ariane 6 heavy lift booster.
JUICE will be launched next year in 2023 in April, the beginning of April. The launch window will open on the 5th of April and will stay open for about 3 weeks because of celestial mechanics. And then the spacecraft, will, before being injected into the transfer orbit to Jupiter, will have to acquire more speed, and we will need to do a certain amount of gravity assist to the inner planets of the solar system. We will do a gravity assist, which will be a first, which will be a Moon, Earth gravity assist. Then there will be a Venus gravity assist, other 2 flybys of Earth, and then will be projected to the insertion orbit to Jupiter for other 2 years. So overall, it will take about 8 years to get to Jupiter.
The gravity assists, 25 in total, will allow the probe to gain the necessary speed to reach its final destinations without consuming the 3,000 kilograms of precious fuel reserved for course corrections and orbital insertions. JUICE will arrive at Jupiter in 2031, followed by a proposed orbital insertion around Ganymede in 2034, all part of the European Cosmic Vision Programme.
The Cosmic Vision Programme has an objective of studying also outer worlds, so it will be complementary to future missions, to mission currently in development, like Plato, like Ariel, like SMILE, and be complementary with the future missions. There will be an Envision for the study of Venus, with Athena, for example, for the study of the universe, with LISA for the study of the gravitational waves. So it will be complementary to have a full and round information on astronomy and planetary science. And it will be also part of the inspiration that the Cosmic Vision Programme wants to transmit to the scientific community and to the public. So JUICE has been developed by a huge industrial consortium to build the spacecraft itself. So in particular, we have Airbus France, which is the main contractor to build the spacecraft, and which is made 95% by European companies. It's about over 100 companies from Europe, and about the 5% of contribution from United States. The JUICE embarks 10 scientific payloads, and the payloads are the contribution from leading funding agency, which are the space agencies. So in particular, we have CNES, there is the Italian Space Agency, DLR, German Space Agency, there is the UK Space Agency, Swedish Space Agency, and we have also contribution on an instrument, another contribution from NASA, as well as from JAXA, and also from the Israeli Space Agency. And each of these scientific consortium is built by other institutions from as well over Europe. So we have also contribution from Austria, from Belgium, from is a European-wide consortium.
Over time, JUICE's orbit around Ganymede will naturally decay. Eventually, there will not be enough propellant to maintain it, and it will make a grazing impact onto the surface in late 2035. JUICE will not be alone in its mission. NASA is also launching a probe to the same local. However, its primary goal will be to study Europa exclusively. The mission is the Europa Clipper. Due for launch 2 years after JUICE, the Europa Clipper will ride a SpaceX Falcon Heavy. This time, the probe will utilize Mars for a gravity assist in 2025, then Earth a year later, arriving in the Jovian system in 2030, a year ahead of JUICE. Due to the harsh radiation environment, the Clipper will not orbit Europa, but instead orbit Jupiter and make multiple passes of Europa, 44 encounters over 3.5 years. Utilizing the other Jovian moons for gravity assists the Clipper, which will adjust its orbit to pass by Europa and various altitudes from 2,700 kilometers to a mere 25 kilometers, where it will be able to pass through the water plumes erupting from the surface. It will carry 9 instruments, including thermal and radar imaging, ultraviolet spectroscopy, and surface dust analyzer.
This allows us to have a mission that's many years long and to collect and transmit lots and lots of data. As Europa orbits Jupiter, it flexes, and we could measure the gravitational change of Europa by encountering Europa at different points in its orbit. On a typical flyby, we would turn on our remote sensing instruments, we would image the surface, we would interrogate the surface with spectroscopy, and we would do the same thing on the way out. And we would essentially rinse and repeat, and do this many, many times until we understand Europa globally.
Because once we will have investigated whether life can be sustained in the icy moons in Europa or Ganymede, then there could be other missions that will go to analyze more in depth if life is really there, maybe with penetrators, with rovers, with sample return missions. And one of the objective also of cosmic vision is to be an inspirator for future missions. Also for a sample return, for example, why not on the icy moons of Jupiter?
It is the closest planet to Earth in size and distance. It once may have had oceans and a similar climate. Now, it is hostile and unforgiving. Scientists want to know why and how it changed. This could help with the hunt for other habitable worlds. For now, Venus could be considered Earth's evil twin. One of the brightest objects in the sky, Venus has been a world of mystery and conjecture. Probes were sent to briefly study the cloud tops as they passed by. The NASA Mariner mission, quickly followed by the Soviet Union's series of Venera flights. They left more questions than answers in their wakes. Eventually, Venera 4 landed a probe through the dense atmosphere onto a searing hot surface, followed up with more sophisticated probes that lived for a very short time. Other probes floated briefly in the dense, poisonous atmosphere. Mars became a much more attractive target, and Venus has been left little explored. In the late 80s, the Magellan probe was launched from the Space Shuttle. It mapped the planet's surface with radar, giving us a detailed look at the rugged surface of the planet. Stripping away the dense, thick atmosphere revealed intricate mountains, volcanoes, and lava fields, an uninviting and hazardous environment hot enough to melt lead. Following orbiters from both Europe and Japan also studied the surface features with radar. The Venus Express dipped into the upper atmosphere to aerobrake and descended into lower orbits. In recent years, several probes have used Venus for gravity assists to propel them to other destinations. Bepi Colombo, on its way to study Mercury, passed by, taking images and other readings. The maneuver, the second at Venus and the third of 9 flybys overall, helped steer the spacecraft on course for Mercury. Another European spacecraft, the Solar Orbiter, also utilized Venus for a slingshot as it closed in on its solar orbit. The Parker Solar Probe made a close flyby, taking measurements of the electric field of the planet and the radio emissions from the hot surface.
It's thrilling to be able to see something that's never been seen before. This emission that we're seeing is thermal emission. Even on the night side, the surface of Venus is so hot that it's glowing faintly at very red wavelengths.
These whisper images, I think, are really exciting because they provide a new window into the lower atmosphere and surface region of Venus where these extreme conditions exist.
A faint glow of heat from the night side shows distinctive features like continental regions, plains and plateaus. A luminescent halo of oxygen in the atmosphere can also be seen surrounding the planet. These observations revealed much about the chemical composition of the surface.
Another really interesting thing we could look for is potentially mineralogical differences. Different rocks and different minerals emit different levels of heat.
Some surprising results suggested that water may have been on Venus in the past, but climatic changes and planetary processes removed the water from the planet and its atmosphere.
We have chemical fingerprints in Venus's atmosphere and on its surface, suggesting that Venus might have been habitable in the past.
The Wide Field Imager, or WISPR, is the sole imager aboard the Parker Solar Probe.
This is something that's truly new, and I believe will yield exciting science in the long term.
Once upon a time, Venus might just have been like an early Earth, with oceans, lakes and rivers of liquid water, a much milder, oxygen-rich atmosphere. What changed the environment? Perhaps volcanic eruptions and toxic gases creating an atmosphere of carbon dioxide and sulfuric acid clouds, trapping heat in a greenhouse effect. Venus has the hottest surface of any planet in our solar system, hotter than Mercury. The atmospheric pressure is nearly 75 times greater than that of Earth. NASA and ESA are returning to the planet to find some answers. Europe is sending the spacecraft Envision, in partnership with NASA, which is providing the synthetic aperture radar system called VENSAR. The S-band radar will also act as a microwave radiometer and altimeter to map the surface. Envision will also carry 3 optical spectrometers designed to observe the surface and atmosphere of Venus, and a subsurface radar sounder that will probe the top kilometer of subsurface. NASA will also be sending Da Vinci and Veritas to Venus, due to be launched around 2029. Veritas stands for Venus Emissivity, Radio Science, INSAR, Topography and Spectroscopy mission. It will also map Venus's surface to determine the planet's geologic history. Germany and France are contributing to the infrared mapper and radar systems to determine whether active volcanoes are releasing water vapor into the atmosphere. Da Vinci, the atmospheric probe, will descend into the Venusian atmosphere to study the gases and chemistry with advanced sensors. It is designed to survive the descent to ground level whilst imaging its journey. The 1-meter wide probe will target a region called Alpha Regio, twice the size of Texas, and will add to scientists' understanding of rocky, atmosphere-bearing exoplanets that will be explored by new observatories such as the James Webb Space Telescope.
So Venus is cool. Venus is awesome. Venus is, in many ways, one of the most Earth-like planets that we know of. One of the key ways that it's different is that it's very, very dry. With temperatures on the surface of 460 degrees centigrade, and whatever that is in Fahrenheit, you would never expect there to be liquid oceans on the surface. That kind of temperature only boils off that water into steam, but the atmosphere of Venus is still incredibly dry, so where did the steam go? So to talk about how we remove something from a planet, we're going to have to talk about 2 forces of nature. Firstly, the force of gravity. Gravity is the thing which is holding you down to the planet, but if you think about it, it's also what is holding the atmosphere down onto the planet as well. If I want to remove some of the oxygen from the planet, we have to overcome that gravity. So to do that, I want to talk about the electric force. It's the thing which your device is using right now to pump electricity around its wires, right? It's pushing the electrons around the circuits. And what we think can happen is that the electric force can help push on the ions and in the upper parts of the atmosphere, push them off and up into space. So just as every planet has a gravity field, we think that every planet has a weak electric field. So we went looking for Venus's electric field, and boy oh boy did we find it. It turns out that Venus's electric field is at least 5 to 10 times stronger than at Earth. It's a monster of a force. It can rip heavy things like oxygen straight out of the upper atmosphere and send them kicking and screaming off into space. So this really changes the way we have to think about planets, because it turns out that planets can lose heavy things like oxygen to space entirely through electrical forces in their ionospheres. This is something that's really important if we want to go looking for exoplanets, for habitable planets around other stars. It is no good having conditions perfect for an ocean and an atmosphere that you might want to breathe if some invisible force is going to come along and rip it all off into space. It's only understanding how atmospheres evolve can we try and understand how we got here.
Many orbiting telescopes and instruments are now in use to search for, identify and catalogue exoplanets, planets orbiting other stars. TESS, Kepler, Hubble, James Webb and the Nancy Roman telescopes are looking at planetary formations around various stars. Knowing how Venus evolved would give additional assistance to the planet searchers. This image is of a new star and its gas disk. The black rings show where planets are forming by gathering the dust and debris. This image reveals a moon forming around a gas giant as it evolves. This massive exoplanet orbits a white dwarf, the remnant of a dead star, and is slowly evaporating.
Another big unknown is to characterize planets that are orbiting other stars. So we could now, astronomers have got very good at finding these planets, but what we want to do is look at what they're made of. So what's in their atmospheres, or if they were rocky, what kinds of minerals are we seeing? And to be able to do that, I think will be stupendous.
So this, we can see the composition of the atmosphere in exoplanet, so what it's made of. And the specific planet we're looking at is hot. And so what we see in that is that there's water there. It wouldn't be in liquid form because the planet's hot, so it would be more like steam that's around it. But we can tell what's in that atmosphere.
So the James Webb Space Telescope is brilliant in a number of ways. One, it extends our wavelength all the way into the infrared, into the mid-infrared, so we can look for these heat signatures from these planets as well. But that also means we can cover the fingerprints of different materials in the atmosphere. So the Hubble Space Telescope looks for fingerprints of sodium and potassium and water in the atmospheres of these worlds. But the James Webb Space Telescope is going to be able to look for signatures of methane and carbon dioxide and carbon monoxide, as well as all of these wonderful water features that we'll be seeing in these giant planet atmospheres. But not only can it tell us in these different wavelength ranges, it's actually better resolution, so we can get more data points for each of these different molecules. And it's a much bigger telescope. We're collecting far more light. We can get a much better precision. So that means that the degree to which we believe our measurements is going to improve a lot with this telescope. And that's going to mean that we'll be able to tell you with confidence what we're measuring. Looking for life on other planets is the ultimate future goal of all of these missions, trying to understand how we got here, how the Earth is the way it is. The James Webb Space Telescope is taking us one step further towards that goal. We're going to be pushing to these smaller worlds where we can see what different planets that are unlike ones in our solar system are like, how atmospheres change with the size of your planet. And it's also going to give us information on these giant planets that we don't have in our solar system, so close to their star that they're hotter than a rocket. They're different worlds that we can explore with this, and every technique that we use with the James Webb Space Telescope is going to be the technique we need to be looking for life signatures on these other worlds. So getting good at using this technique is so important so that in the future we can be looking for these signatures.
So what we see here is what's called a hot Jupiter. So it's a planet that moves in front of its star, and it has about the size of Jupiter but the mass of Saturn. And what we see here is light filters through its atmosphere, and that allows us to look for the fingerprints of certain molecules. And in this case, the planet is full of water vapor, full of water. And that's what you see as wiggles in the spectrum. When we go and look at other exoplanets with Webb, we may look for other molecules, some that are familiar in our own atmosphere here as well, like carbon monoxide, carbon dioxide, or maybe even methane and ozone.
The total so far exceeds 5,000 exoplanets, with a further 8,000 to be confirmed. Of particular interest are the smaller, rocky, Earth-like planets.
We know our targets. They're bright stars which are known to host the type of planets we want to observe, and we will know when these planets transit. That is, when the planets move across the disk of the star, and we can measure the changes in the output of the star, the measured output of the star, in order to measure the size of the planet. we'll be focusing on smaller planets, so Earth-sized to Neptune-sized planets, which have been found by other missions, such as Kepler, to be very abundant around other sun-like stars, something which is not so much the case in our own solar system. So it's a big question. What are these smaller planets? What are they made of?
The range of planet types is amazing. Rocky worlds that sustain oceans and lakes, likely candidates for life. Others more extreme, like WASP 76P, tidally locked to its star, only ever showing one face to its sun. This extreme exoplanet has a day side where metals evaporate and a night side where it rains iron. Rogue planets that have no sun to orbit, ejected from their solar system and left to roam through space. Planets that have the heavy element barium in their atmosphere. Water worlds, planets still forming, others around dying stars. We must remember that amidst all these searches for a new Earth, we must take care of the one we have, because it is a very long way to travel to reach these other habitable worlds. Two advanced space probes are now orbiting the Sun, one from NASA, the other from Europe. They have begun studying our star up close, imaging the mechanisms of hot plasma and magnetic fields, even diving into its atmosphere, discovering new insights into the solar winds and the science of the stars. This is the Royal Observatory of Belgium in Brussels. Scientists have been studying the sun from here for over 100 years, using telescopes like this. The observatory is also the World Data Centre for the Sunspot Index. It is now receiving data from the European Solar Orbiter, a wealth of information studying the sun up close, well within the orbit of the planet Mercury. The imagery alone is spectacular, giving us a whole new perspective of our sun and the nearest star.
It sometimes happens, I get into my office, I download the latest data and I stare for hours at it. It's so addictive actually. Nobody has ever seen the details of the corona in that much detail before. So every time we get an image down, it's the first time we see something at that scale, and that's really fascinating. It's really discovery space that we're entering.
I was personally blown away by the quality and degree of detail in these images. And clearly, as solar physicists, we've been looking at images of the sun for many years. But by going 3 times closer, we can get the spatial resolution up by a factor of 3. And we see things that we haven't seen before. And that's, of course, the beauty of science, to explore the unexplored.
The journey of Solar Orbiter began in 2020 and has travelled over 2.5 billion kilometres, with gravity assists from Venus and Earth.
The spacecraft is performing very well, and we are very happy about that, because it is the first time that it had to go so close to the sun, and so in this very challenging environment. And of course the spacecraft is designed for it, but this design is all based on modeling, on predictions, so you only really know that it's going to work until you have seen it working.
Solar Orbiter is basically a research mission, but ultimately we want to be able to predict space weather. These are energetic events that could have an impact on high-tech installations on Earth, GPS satellites, power grids. And we want to make sure that in the future we can predict geomagnetic storms based on solar activity. And for that we really need to take the sun's temperature and measure the solar wind and connect the two. By going close to the sun, we try to capture the physics of space weather events, and we want to film on the sun the events that give rise to changes in the near-Earth environment. And we need to fly close to the sun to be able to measure the solar wind while it's still in a pristine, undisturbed state.
One of the great mysteries of the sun is the difference in temperature from its surface to its atmosphere, where it increases by 1 million degrees in a process that is not yet understood. Generation of the high-speed solar winds emanating from the star is another process under scrutiny.
For the mission, it's important in many ways, because on one hand, of course, the closer you go, the better resolution you get and the more details you can see. And it's also important because we want to understand the influence of the sun on planets, on the Earth. And for that, we want to come closer and we want to see what's happening and at the same time feel around the spacecraft how the environment is changing.
So the EUI, so the Extreme Ultraviolet Imager, sees the hot corona, so to speak, the atmosphere of the sun at extremely high resolution, much higher than what we had before. And one of the problems that we are after is to understand why the corona is so hot. It's like 1 million degrees or so, while the surface of the sun is 5,000, something like this. And that's really puzzling, and we're after that since decades. And we think that it's possibly because of tiny, tiny, tiny eruptions that go on all the time, but that are small, too small to be seen by other instruments. And now that with Orbiter we get so close to the sun, we can finally see them. And we did see a lot of them in the first images that we took. And the closer we get, the more we see. So we are really excited about this because we may finally be on the solution to that decade-long problem.
These measurements that the spacecraft is taken now and also later will be important to improve our understanding of the Sun. One of the things we want to understand better is how the Sun affects the Earth, but for that you have to really understand how the activity of the Sun is caused, how it evolves, and when, for example, such a cloud of solar material leaves the Sun, how it also propagates through space and goes towards the Earth. So for that we want to do several of those close passages to the Sun to observe it from close by, and we also want to change the orbit of the spacecraft so that it can see the solar poles, because we have never ever seen those before, and they are important to understand the magnetic field of the Sun.
The solar orbiter carries 10 instruments on board. Imagers of various frequency, including an X-ray spectrometer and extreme ultraviolet imager, a magnetometer energetic particle detector, and a solar wind analyzer suite. It also carries a radio and plasma wave suite, which measures electric and magnetic fields around the spacecraft.
So now the whole payload is working together. It's actually a lot of work to coordinate all that. But what that gives us is that we get a comprehensive diagnostics of the solar plasma, of the solar atmosphere. So we can, with EUI, get the dynamics, the fine scale structure, but then with other instruments like SPICE, we can get measurements of the temperature, of the density, these kind of things. So with all the instruments together, we get a comprehensive view and understanding of the physics. And then you have all the in situ instruments also that we are working with that will help us understand what the coronal mass ejections are and how they influence the physics of the heliosphere, which is the surroundings of the Sun, so to speak.
By having all 10 instruments on Solar Orbiter operate together, we can really harness the entire power of this mission, which is designed to connect remote sensing observations of the Sun, meaning pictures and spectra, and what you measure, essentially feeling the solar wind as it flies past the spacecraft. And for that we need all 10 instruments, and they've now all been tested and exercised and tuned like musical instruments. And so this is the first time we actually got all 10 working together as a team.
So this solar orbiter and the instruments on it, it's a new machine that we are bringing to a place in the space that has never been visited before. So when we do that, we cannot expect everything to work as it is designed or is expected. There is a steep learning curve to learn to operate the thing, and that's what we call commissioning phase. And we're now at the end of that phase, and we have learned how to operate our machine to the best of its capacities, and the results are actually fabulous.
It's important to have all the instruments working and operating in a coordinated way, because one of the main goals of the mission is to link the Sun and its activity with the environment, and not only the environment close by, but also the planets. And for that we want to look at the Sun's activity, at the solar activity, with many different telescopes that look at it in different wavelengths. So that means they are looking at different layers in the atmosphere, and they can also measure things like the magnetic field on the Sun. And then at the same time, we also have instruments at the outside of the spacecraft that will sense and measure what's happening around the spacecraft itself. So whenever there is solar activity, we can feel the effects close to the spacecraft.
Among the things that we now see for the first time are really tiny sources of energy release in the corona. And we are now very curious to find out in what sense they are connected to the large-scale structure of the solar wind and the energy that gets essentially put into the flow of particles towards Earth. And we try to really use models to connect what we see on the surface to what we see in the wind. And that is something that clearly takes more time and investigation to really pinpoint where a solar wind package came from. But we believe that we've done quite well in terms of pointing at the right place, and thereby we hope to get this complete picture of cause and effect. Close approach of solar orbiter to the Sun, to about a third of the distance between Sun and Earth, is so important because it allows us to get measurements of the solar wind in an almost pristine state before it gets mixed on its way to Earth. And more importantly, to combine these measurements with pictures of the Sun and spectra that we can then connect and get a complete picture of the Sun and solar wind.
Scientists are also studying the dangerous solar storms that affect Earth.
This first perihelion was clearly our first scientific milestone after getting all the instruments calibrated. So this really gives us good confidence that we'll be able to do this again, and we'll do it roughly twice a year when we fly by the Sun again. In between, we'll be far away from Earth, so that takes a lot of time to get the data downloaded. But in between these far away periods, we have also close by periods where we can dump all the data that we've accumulated, and then it's Christmas for the scientists to look at the data and get new scientific insights.
The Parker Solar Probe is the second spacecraft now operating close to the Sun. It was launched by NASA in 2018 and has taken 4 years and several gravity assists to reach its operational orbit. Its elliptical orbit bringing it closer and closer to the star's corona, a boundary layer not clearly understood. This project has been over 50 years in the making.
The fact that the Sun is hot has been a major technological challenge, and why it's taken us so long to fly Parker Solar Probe.
That design of the heat shield, where the front of the heat shield that faces the Sun is hot enough to melt aluminum, but the backside, where the spacecraft electronics and instruments are, is actually at room temperature. That's been the key to getting this mission done.
This is a dream come true. One of the major goals for the Parker Solar Probe mission is to fly through the solar corona, and we are doing that now.
The edge of the Sun's atmosphere is known as the Alphen critical surface, a postulated zone where the solar wind goes from a slow to extremely fast speed, spreading out through the solar system. The Parker Solar Probe has passed through this barrier into the corona, showing that the boundary is indeed lumpy and has sampled material still bound to the Sun.
Two of the most challenging scientific mysteries in astrophysics occur in a region that we call solar corona.
The instruments on board have shown that outside the boundary, the solar winds accelerate away from the Sun at high speed, unable to fall back onto the surface. However, inside the boundary, the magnetic field is much stronger, and solar material is much slower, tied to the surface.
That we've always known that the atmosphere of the Sun, the corona, spins with the Sun, spins at the same speed that the Sun does. But out at the Earth, the solar wind is moving straight out from the Sun, so it's no longer spinning. Where that transition happens is very important for understanding, because that spinning of the corona actually helps slow down the sun. All stars get slower in their spinning as they get older. Parker Solar Probe sees that that transition from spinning to straight happens further from the sun than we thought. And that actually has implications for every star in the universe and how they slow down. And that's important actually for the habitability of solar systems around distant stars.
Gaining knowledge of our sun will help us understand all the other stars around us. This will help us with the search for habitable exoplanets. Understanding the processes of the solar winds and energetic particles will assist with finding worlds that, like the Earth, have magnetic shielding to help protect living organisms on the planet's surface.
Parker Solar Probe is the first mission to get close enough to the sun to see where the action is actually happening, where the solar wind is accelerated, where the corona is getting heated. And we've seen a lot of new science that we don't completely understand, but there have been some remarkable results about small events that we can see in Parker Solar Probe that get smeared out in the 93 million miles between the Earth and the sun.
We are so excited for these new results coming down from Parker Solar Probe. Parker has gone closer to the sun than we've ever gone before. It's inside the orbit of Mercury. We're seeing the solar atmosphere as it emits its material out into the solar system. We call that the solar wind. And we're seeing this process up close and personal at a higher detail and complexity than we've ever seen before, actually as it's being formed. So we're able to study the solar wind and all of its variability and complexity up close like we just can't do from Earth.
The protective magnetic field surrounding Earth is constantly buffered by solar winds and energetic particles. At the poles, these solar disturbances create spectacular auroras. It may also cause the atmosphere to leak out into space.
So the sun not only has this constant solar wind that blows out in all directions, it has solar storms, solar flares, and coronal mass ejections. And those energetic storms can accelerate particles up to almost the speed of light. And those energetic particles can actually cause radiation sickness in astronauts if they're out unprotected when those happen. On the Earth, we're protected by the Earth's magnetic field and the atmosphere of the Earth. But once you're out in space, away from the Earth's magnetic field, those can be a danger to not only astronauts, but also spacecraft.
The sun is capable of energizing pieces of atoms up to really high speeds and energies, and these are damaging to astronauts and to electronics. Now, we're protected down here on Earth from these particles, but on the moon or beyond, astronauts wouldn't have that luxury. So one of the key missions of Parker Solar Probe is to understand how these particles are actually being accelerated so that we can better predict and protect against them.
Another phenomenon of our sun deals with space dust and debris, pieces that clump together by static electricity, and then, as they grow by gravity, there appears to be none close to the sun.
Space dust is pieces of comets and asteroid debris that fills our solar system, but close to the sun, they can be so hot that they actually vaporize, or that material can also be pushed away by the radiation of the sun. And so there ought to be a region around the sun where there is no dust. And for the first time, Parker Solar Probe is seeing evidence of this dust-free zone.
So the sun goes from a quiet period, what we call solar minimum, to solar maximum, and back again about every 11 years. And we launched into a very quiet solar minimum. That's actually helping this mission, because during solar minimum, things are simple. There aren't very many sunspots. There aren't very many of these solar storms. What ones we're seeing are small, and that allows us to individually identify every single event.
And then later, as Parker continues to observe the sun, we'll see this ramp up of activity and energy bursts, and we'll be able to see the more complex and bigger energy bursts.
In the coming years, the probes will witness up close the power of the sun during its more active phase, as it spirals closer and faster to the star.
Parker Solar Probe is already the fastest human-made object. As it gets closer to the sun and spirals in and goes faster and faster, it will reach 500,000 miles an hour. So we are so excited to see the results as Parker continues on its mission.
Before Parker Solar Probe passed through the sun's Alphen boundary, it detected kinks in the solar wind, where it would momentarily double back on itself. Scientists call them solar wind switchbacks, but had no idea of the mechanism that caused them to form. As Parker got closer and closer to the sun, it detected more and more of these switchbacks. It was able to track one of them to its origin on the visible surface of the sun. On the surface, you can see defined cells as heat rose from beneath. These convection cells churned and created funnels of magnetic energy above the surface. Scientists concluded that these switchbacks form inside these funnels before rising into the corona and beyond. This is only one piece of the puzzle. However, scientists still don't yet know how they form. Over the next few years, Parker will keep looking for clues as it explores our sun up close. The sun is the only star we can study like this. It is also the only star we know that supports life on at least one of its orbiting planets. Understanding it is critical as we search for life beyond our solar system.
That will link directly into the question, are we alone in this universe? And that is one of the biggest questions for humanity to answer.
Asteroids, remnants from the birth of our solar system. From planetoid-sized monsters down to tiny pebbles, they have orbited our sun for billions of years. We have seen some up close, even touched their surface. We count their numbers, chart their courses, and keep a wary eye on these mountains in the dark. Several spacecraft have ventured out towards these rocky worlds. Some have touched down and taken samples with surprising results, then returned them to Earth. Scientists have found these remnants to be complex and full of secrets. There are different types of asteroids. and 2 new robotic probes are ready to study some of these unique targets. One is called Psyche, and it is perhaps one of the most interesting.
16 Psyche is an asteroid that orbits the sun out between Mars and Jupiter. It's called 16 Psyche because it was the 16th asteroid discovered, and they were all being named after gods and goddesses at that time.
So the Psyche mission is going to visit an asteroid which is called Psyche. And it is a large metal asteroid, a unique body in the solar system, 150 miles in diameter approximately, and made of 40 to 60% iron nickel metal. That makes it a unique body in the solar system. We visited worlds made of ice and worlds made of rock and worlds made of gas before, but we've never visited a metal world. So we'll get to see something unique and different for the first time.
All the rocky planets that we know of, the Earth, Mercury, Venus, Mars, and the Moon, all have got a metal core in their center. And especially for the Earth, it's the source of our magnetic field, which may be tied to holding onto our atmosphere and making our planet habitable. There's a lot of study that's going on to understand that. But we don't know a lot about our core. What we've learned about it, we learn indirectly because we can't go there. And so Psyche gives us the opportunity to visit a core, the only way that humankind can ever do. And so we hope to learn something about what's inside the Earth and other rocky planets by visiting Psyche. But it also tells us about the processes in the very beginning of the solar system. It helps us understand how planets form in the first place.
So the Psyche payload consists of 3 science instruments. One of them is what's called a gamma-ray neutron spectrometer. It's actually 2 separate pieces of hardware. One is the gamma-ray spectrometer and the other one is the neutron spectrometer. Both combined study the elemental composition of Psyche.
If you know the surface composition, what it's made of in terms of iron and nickel and silicon and oxygen, you can then start to say something about its history and how it formed and how it evolved.
By using gamma-ray spectroscopy, we can measure those elements remotely. We don't have to touch the surface. We don't have to dig into the surface.
For Psyche, we're building kind of what we call the Cadillac. It's a very high precision, high sensitivity instrument. It's very similar to the Messenger instrument.
That technology that we developed for the Messenger spacecraft gave us a huge head start going to Psyche.
For our types of instruments, we don't get to fly them very often. So when we actually get selected for something, that's a big deal for us, where we can, take what we learned from the prior missions and implement it now and make an even better instrument.
Only one body like this that's this big and made of metal in the solar system. So the big mystery is, where did it come from? How was it created? One of the theories about it is that it was once the inside of a forming planet, because the planets that we know, Earth, Mars, Venus, Jupiter, have metal cores inside of them. So this may have been the metal core that was forming inside of a baby planet, which then collided with other planets that stripped off, forming planets that stripped off that rocky mantle, just leaving a piece of that core in space. And if that's the case, then by studying this body, we'll be able to study the cores of planets like our own, the Earth, in a way that we can never do otherwise.
Psyche is a larger asteroid in the main belt that is in between Mars and Jupiter. Our experience so far in terms of exploring the solar system has been with either rocky or icy bodies. What's particularly interesting about Psyche is we think it's a metallic object. We have a common understanding perhaps of how regular common rocks behave, but metal behave in a very different way. What I contribute to the mission is trying to understand how cratering and the process of collision and interaction work for a metallic object. And we will use this information then to understand what we see at the surface once we get there. What we did is take an iron meteorite, put it in the chamber, and use it as a target for our input experiment. And we were shooting a quartz bead at high speed in order to produce a crater. Everything has been filmed with high-speed cameras, so we have a tremendous amount of data that shows in high resolution what happened during the contact, during the explosion, and how the crater forms on the surface. So everything has been documented in great details. Here we have a piece of the Gibeon meteorite, and what we see here is a crater that was produced as a result of one of our experiments. And traditionally with rocks, the rim would be blasted away and would be a sort of flattish feature. But here we see these flaps that basically are frozen into place, and this is because the metal is much harder than rocks, and so you can then retain this interesting morphology. There's going to be a very exciting phase of the mission when we actually start gathering data, and there's going to be lots of surprises. I just can't wait to be there and see whether or not there is, any resemblance with this model or not.
There is nothing like the experience of sitting on console on launch day and hearing all the people go around and say, we're go for launch, and then finally getting to say yourself, we are go for launch. It's the culmination of all those years of effort and all those hundreds of people working, and so it's super exciting when you actually, finally say, we're go, and we're gonna get that beast into space. We're going to go launch and do a Mars gravity assist, go by this planet Mars, and then continue on to the asteroid using electric propulsion.
I think no matter what we think it is right now and how much we hypothesize what it might look like, I think it's going to really surprise us and change our views about our solar system when we get there. And that's it's an incredible opportunity to be a part of the team making that happen.
The Psyche mission has suffered several launch delays. However, it should be underway in the next year or two.
Three, 2, 1, 0. Liftoff. Atlas V takes flight.
Another ambitious mission that has launched is Lucy, to study several asteroid targets.
Tower clear.
So Lucy is going to survey 8 asteroids over a 12-year mission life. The first asteroid is in the main belt asteroids. It's Donald Johansen. And then the remaining asteroids are the ones that we call the Trojans. And because we believe that they are remnants of our solar system, by studying their geology, as well as their composition and their mass, then that will give us insight into planets, planet formations, and in particular the outer planets.
The Trojan asteroids, which are located in these Goldilocks zones of gravity-stable orbits in between the Sun and Jupiter, are really leftover fossils from the formation of the solar system. And these fossils are around 4 billion years old, and when the solar system was forming, they were brought into these locations. And the Trojan asteroids, which have been there since the formation of the solar system, are these last unexplored remnants from the cosmic neighborhood creation. And we're extremely excited to go and visit them because of our total lack of understanding of exactly what is out there. And so it's going to be extremely exciting when the Lucy spacecraft explores them.
Some of the most important planetary science questions we're trying to answer are focused on the origin and the evolution of the solar system. Asteroids and other small bodies are really important keys to understanding that history. Amazingly, many of these mysterious worlds have been altered very little in the 4.6 billion years since they first formed. Their relatively pristine state makes comets, asteroids, and some meteorites wonderful storytellers that have preserved clues they can share with us about conditions in the early solar system. In particular, by studying the Trojan asteroids, we can gain more insight into the history of the outer solar system and the giant planets, Jupiter, Saturn, Uranus, and Neptune. We actually find asteroids across the solar system, including near-Earth asteroids that are in orbits that periodically bring them close to Earth, main belt asteroids that orbit the Sun between Mars and Jupiter, the Trojans that Lucy will explore, and the Kuiper Belt just beyond Pluto, which contains some of the most primitive objects in our solar system. Not all of these asteroids are the same, and Lucy is part of a collection of ambitious missions to study the diversity of these asteroid populations that will help us fill in more pieces of that cosmic puzzle.
Lucy will slingshot out from Earth's orbit and pass by the first target, a C-class or carbon-based asteroid named Donald Johanson after the famed archaeologist. Lucy will continue to the orbit of Jupiter and intercept 4 more targets: Eurybates, Orus, Lucas, and Polymele. Some are D and P class asteroids never seen before and theorized to be rich in volatiles and organics. The probe will then return to Earth for another gravity assist to the trailing Trojans of Jupiter, intercepting the twins Patroclus and Menetius, more P-class objects.
And Lucy spacecraft was named after the Lucy fossil because we will be studying asteroids, which are the fossils of planet formation. But the Lucy spacecraft and the Lucy fossil was named by archaeologist Donald Johanson and his team because apparently when they discovered the hominin, they were listening to the Beatles song Lucy in the Sky with Diamond. Now we do have a diamond. It's our beam splitter, which is on the L-test instrument, which is used to split the beam, is actually made of diamonds.
My job as a mission architect here at Lockheed Martin, it's very interesting, and it sort of encompasses the biggest picture of the mission. What is the trajectory? What sort of propulsion do you need to fly that trajectory? What does the spacecraft look like? So in the case of, for example, Lucy, it's like, okay, it's going out 5 times further from the sun than the Earth is. And so it's going to need big, huge solar arrays just because of that.
Lucy has 3 scientific instruments on board the spacecraft, and we'll also be using 2 of the spacecraft subsystems to contribute to the science investigation. With the LORRI instrument, we'll be able to get panchromatic images, which will tell us about the geology, and the crater history, which gives us the age of the surface. With the TESS instrument, we'll be able to measure the temperature of the surface at different points, and with the RALPH instrument, we'll be able to measure the composition of the surfaces. The Jupiter Trojans, they have a variety of surface characteristics. They have different colors and different surface compositions, and that leads us to believe that maybe they formed somewhere else.
After launch, the Lucy probe failed to lock one of its solar panels in place. Engineers are working on a resolution to this problem.
The Lucy spacecraft will travel 4 billion miles over its mission. And it is a very sophisticated, well-orchestrated trajectory that gets us there.
I cannot wait for those gorgeous images that our instruments are going to take and bring back to Earth. What that's going to tell me and the world is how gorgeous these objects are, what secrets they have to hold, and it's going to start us unlocking these mysteries of the solar system that are out there. I can't wait, and words can't describe just how excited I am to share with everyone these images when they first come back.
This animation is drawn from the recent data release of the ESA Gaia satellite. It reveals the locations of the larger asteroids within our solar system. This tapestry of orbits shows that several near-Earth objects cross our orbital plane. Geological history records that some have hit the Earth with devastating effects.
We've seen asteroids come through the atmosphere and kind of explode and cause some damage. And thankfully, so far, nothing recent enough that it really has a large impact on our civilization, but it could happen.
There are multiple different ways that you might attack the problem of, oh no, doomsday asteroid is inbound. One of those ways is a kinetic interceptor, which is what DART is working on.
As part of planetary defense, DART, which stands for Double Asteroid Redirection Test, its mission is to impact an asteroid in a binary system.
The reason we're doing this test is to try and prove out the technologies that would be needed to, say, save Earth if an asteroid were coming our direction and we needed to adjust its trajectory so that it would miss the planet.
SmartNav is the autonomous algorithm on board, and the purpose of SmartNav is to identify Dimorphos, which is the smaller of the two asteroids in the Didymos system, and we send maneuver commands to the spacecraft for the spacecraft to hit Dimorphos.
And we understand where about 40% of those asteroids are. We know that no known asteroid is a danger to the Earth right now, but the concern is about the asteroids we don't know about yet. And if we should ever discover an asteroid that's on a collision course with Earth, we want to be able to discover this years in advance so we can give the asteroid a push, not to destroy it, we probably wouldn't be able to do that anyway, but just to prevent that collision. And the DART mission, the Double Asteroid Redirection Test, is our first test of one way of doing that.
Launched aboard a SpaceX Falcon rocket, DART is well on its way to its target.
So the way an ion thruster works is that it utilizes electrical energy to ionize propellant and accelerate it using electric and magnetic fields. What NEXT does is that it increases the power level, you get more thrust out of it, it's more fuel efficient, it lasts longer, basically kind of improves things in almost every way and makes it very beneficial for end users to utilize.
When they're rolled out and fully deployed, they're almost 10 meters long. This is the last time that anyone will ever see these arrays fully deployed. Once we stow them here at DSS, they will not be deployed again until we're in space on the DART spacecraft. Part of our detailed inspection entails Andrew looking at the cell by cell on these arrays, again, that are almost 10 meters long. He'll look at them at different wavelengths of light, different angles, just to assure ourselves that we've found every anomaly possible in these cells and they're fully characterized with the entire array, and we know exactly what we have and the condition it's in when we launch.
DART's going to a binary asteroid, a double asteroid, for two really good reasons. The little asteroid, Dimorphos, which is in orbit around the big asteroid, Didymos, that asteroid is about the size of object that we would tend to be concerned about. The most abundant asteroids are the small ones, and this one, about 160 meters across, or about the size of a football stadium, is large enough that it really would cause severe damage if it struck the Earth. Now, by
impacting, by doing our experiment, a kinetic impact experiment on the small moonlet asteroid, we're able to measure our effectiveness in deflecting the asteroid by watching the change in the orbit of the little asteroid around the big one. It makes that measurement a lot more precise and a lot easier to do with telescopes on Earth. The other reason we're doing it is that the presence of the large asteroid there keeps the little one in orbit around it as the pair go around the sun. So that means that this asteroid, which is not a danger to Earth now, will never become a danger to the Earth because of anything that we do in the DART mission. DART is carrying a small CubeSat. It's called the Licia Cube. It was contributed by the Italian Space Agency, and its job basically is to watch the impact from a little distance away. It's riding along on the DART spacecraft, and it's going to be deployed a few days before the kinetic impact. It's going to maneuver and offset itself to the side so that it doesn't run into the same asteroid that DART is running into, and it's got 2 cameras on it that are going to try to first catch the actual impact of DART on camera, but then more importantly, see the ejecta, the plume of material that's blown off the surface of the asteroid and how that develops. If we're fortunate, we'll be able to see the impact crater newly formed by the DART impact. And then, of course, Licia Cube is going to do something that DART can't do, that is fly past the asteroid, look back, and get the full 3-dimensional shape of the object that we hit, which we won't know until we actually get there.
One other threat to Earth is the interstellar object passing through our solar system. They arrive without warning, fast-moving and having no known orbit. Another hazardous mountain in the dark.